Without any further ado, I think this is going to be a pretty interesting talk, sharing some interesting insights into scaling things up to enterprise level security considerations. And so really, if you'd put your hands together, please welcome Eknath and Frank to the stage. Thank you.
Hello. Before we get started, I'd like to remind everybody that attack is cool, but defense is what pays the bills, and enterprise, of course. So because of that, we are really interested in monitoring threat activity and security misconfigurations in our enterprise environments. And every enterprise is unique in its own challenges and use cases. So you kind of end up needing a sort of a custom solution. In this session, we'll provide some insights into our journey of creating such a custom solution, and the problems that we faced and how we address them. More importantly, we're hoping that this serves as a sort of a blueprint, a set of design choices that we made in order to make the solution efficient, scalable, and something that works. And let me introduce us, the team behind the creation of this tool. This is Frank, who initiated this project and laid its foundations, essentially. I'm Eknath. I currently maintain and oversee improvements to this project. Our combined experiences from understanding the lay of the land to essentially refining the end product is what we are excited to share today. So going from first principles, we'll start with the requirements for such a security visibility tool. And I mean, what the essential expectations from this tool are, what the limitations we encountered from off-the-shelf tooling. Following that, Frank will go deeper into a case study of our custom solution. And then finally, we'll talk about the metrics, achievements, and close it up with the ROI. So let's start with understanding security visibility. In our specific case, we had 3 use cases. We had threat monitoring, we had compliance, and vulnerability management. In the threat case, you essentially need to know what processes are running where, what sort of activity is going on, like what sort of files are being created, where these connections are leading to. In the compliance context, it was mostly about capturing evidence, which means capturing configurations, stuff like how many root users exist, what the network interface card configurations are on every single host, stuff like that. In the vulnerability management context, it's mostly the SBOM related material, like what's the name of the package, what's the version of the package, and which host these are installed in. Now, because these hosts are the source of truth, it makes a lot of sense to collect the information directly from here instead of from the static configurations themselves. With that, we also had a couple of tenets to follow. It had to be efficient in the sense that it should not consume more resources than a particular threshold so that it does not interfere with the business applications themselves. It should be It should be very reliable because it is the single source of truth for all of this information. So if it were to break, then vulnerability management, threat monitoring, and compliance would break, so we can't have that happen. And then it should be able to monitor a large fleet. By large, in our context at least, we mean a little over 100,000 hosts. And then we have fairly custom infrastructure, and this solution needs to integrate well with it so that the ops and the DevOps folks, they don't have to do extra work in order to maintain and run this tool. And lastly, we need the data to be accessed and analyzed by a variety of teams. So the solution has to be fairly open and follow standard protocols. All right, so coming to the sort of high-level limitations of off-the-shelf standard tooling, It's one that we realized that it was getting quite expensive at scale. And I think the at scale part is quite important to highlight here, because if the scale is not too high, then I think off-the-shelf tools, especially from a cost perspective, make a lot of sense. Secondly, like I said in the previous slide, that our infrastructure handling is quite custom. So it was getting hard to integrate and operate into this environment. Then the data gets, I mean, because off-the-shelf tooling is meant for like literally everybody, they cannot propose how the data should be accessed. So they provide typically a unified UI solution, which makes exporting and programmatic access of this data sort of hard, a second-class citizen, if you will. So that is a problem. And then from the data collection standpoint, there are two more problems that we encountered, which is the ability to customize and the ability to optimize. For example, we have servers that we don't really care for how, how often a certain process has run, or if the processor has run thousands of times or creating thousands of DNS requests, things like that. We'd like to deduplicate this data. So modifying all these sort of minutia is, we found that it was quite hard in the off-the-shelf solutions. I would like to talk about the opposite of this, meaning building your own solution. Second point onwards, everything else is exactly the inverse. But the first point, the expensive at scale part, specifically the licensing bit is gone, but it is replaced with engineering time though. So to each his own. And with that, I'll hand over the stage to Frank to talk about the case study.
So I'm going to talk about the technical aspects of what makes a visibility solution, and I'm going to use our own as an example. Ours is called Bigfoot, as you see. So pretty much all visibility solutions would have at least three main components. Try to do this in the diagram here. On the left, we have the data acquisition, so that's just typically an agent that gets the data from a host or a node or whatever. Then in the middle, we have a layer where we receive the data and aggregate it. And then, of course, we have the storage as well, just to make it usable in a way. Now, in our case, the storage is actually where it differs quite a bit from a vendor solution. Ours is meant to be open, so accessible by many different tools. I have put a few examples on there, but this is not limited to those. So we want to gather the data. We want to make it accessible to standard tools. We don't even have a UI like many other commercial tools. I'm going to dive into each of those three layers, like on a technical level, much deeper, starting with the data acquisition on the left. But before I can talk about the agent itself, I have to talk a little bit about eBPF, because it's a critical component of the solution. So eBPF is a Linux feature that allows loading of probes, they're called probes, little programs, functions, into the kernel at runtime by a user space program. So you can load a tiny little bit of code into the kernel. It gets attached to a function, a syscall, a trace point, or anywhere in the kernel, really. And whenever the kernel hits that function or trace point, it will execute that probe, that little bit of code. Now, you may be thinking that injecting code into the kernel at runtime sounds kind of dangerous, but this is not a kernel module, so it's not meant to be able to crash the kernel in any way. So it's perfectly safe, or it's supposed to be perfectly safe. There's a little caveat at the bottom. Now, to give you an idea what BPF usually, like, people say that BPF to the kernel is like JavaScript to a browser. That's largely correct, but it's not 100% true, but it gets the point across, I think. Now, why are we using BPF? We use BPF to capture events from the kernel. So when I say events, I mean a process opened, a DNS lookup was made, a file was accessed. These are, when I say events, that's what I mean. And BPF is reliable, and it is also the most efficient way to get data out of a kernel, at this point anyway. Now let's briefly look at what's necessary to get BPF code into the kernel here. So we start off with a little bit of C code that typically is C. Doesn't have to be, but it often is. When I say C, it is like syntactically C, but there are a lot of restrictions on BPF code, so let's call it restricted C, I think, at this point. This C code is then compiled into BPF bytecode with the standard tooling LLVM. Should highlight here that if you had used BPF in the past, you may have had to install like compilers and the tool chain onto target hosts, but that's no longer the case. We can do this during a build now. There's no need to deploy a compiler and the kernel headers to all the targets anymore. So this can happen at build time with modern kernels anyway. Now, once we have the BPF bytecode, then we need to load it into kernel. This could be done with low-level syscalls, but using a library is way more convenient, of course, for this. So we use the Cilium library because our agent is written in Go. That works quite well. Now, the library would then take the BPF bytecode, send it to the kernel to be loaded. At this point, this is where the kernel then applies some checks. It will run it through a verifier to ensure that the code is actually safe. So it will look for things like unbounded loops, unsafe memory access, and reject any probe that uses that. So once the BPF probe is found to be safe, it then gets loaded into kernel and attached to whatever point in the kernel itself. So, and once it's attached, then it will of course be executed as that code that it's attached to gets run by the kernel. BPF probes are usually stateless. But they do have, there are BPF data structures called maps that can be used to maintain state or to send data into user space, which we are going to, of course, use quite heavily, actually. BPF is quite a large topic, and I'm just scratching the surface here. I don't want to go into too much detail, so I left some resources there if you're interested. Now, let's look at how we use BPF in the agent. So our agent has two methods of getting data from a host. The first one is obviously eBPF. As I just said, it would inject a probe into the kernel. The probe would run when an event happens, and it would exfil data out of kernel space into user space. And the second method is a much easier way that doesn't involve the kernel, like not directly anyway. That's just, we call it scheduled jobs. Those are just functions to read configuration of a host. Configuration could be things like the user accounts that are set up on the host, configuration of NTP, all the packages that are installed, that sort of thing. This data collected in either way will then be enriched. And there's a pipeline, it gets enriched and gets converted into a protobuf, and then it gets sent off the host to the central place. In this case, we use gRPC. Why we use gRPC, I will talk about later. Since we talk about implementation here, I just want to mention that this agent is written in Go. It gives us a reasonably low-level access to everything. It has excellent library support for BPF libraries and gRPC, protobuf, all of this is well supported. The concurrency is very simple, so that's great for performance. And last but not least is Go binaries are just standalone single files. That's a great feature to have in a visibility solution at scale, because it makes deployment so much easier. Having just a single file to roll out into a very large fleet, it helps. Nobody wants to manage Python dependencies on thousands of hosts. So Go fits quite well for us. I mentioned enrichment here, just briefly. I'm going to dive into that a little bit more, into the pipeline here. Enrichment means adding context or metadata, process metadata specifically, to events that happen in the kernel. So let's say there's a DNS event that happened on a host. It's not usually enough to know that it happened on a specific host. You need to know where it came from. Specifically, which process made that DNS query. And even further, we want to know which process made that process that made the DNS query. So the whole ancestry is useful as well, up to and including PID1 if possible. So I have put a little bit of an example here of a DNS event on the diagram here. I'm going to walk through it, through the full pipeline real briefly. So on the left, the white box that shows represents the UDP send function inside the kernel. And I tried to put a BPF probe on top, so that should signify that there's a BPF probe attached to it, meaning whenever the kernel calls a UDP send function, the BPF probe runs first. So that would, of course, be called for a DNS query. The BPF probe would then walk the kernel structures. It would extract the timestamp, the PID of the process that did it, and the raw packet, as it is on the wire, the raw DNS packet. This data would then be sent to user space via a ring buffer. This is a type of BPF map that allows sending from kernel space into user space. It also preserves ordering, which is quite nice. So at this point, we have raw data in user space, basically. The kernel carries on doing its thing. It's no longer involved. But we have this raw data. Now we need to do something with it. The first thing that happens is enrichment, meaning we attach process information about this event, meaning the process that did it plus all the ancestors to it. All of this will be, you can see it there in the middle in the white box. So now we have still raw DNS data, but we know where it came from. At this point, the ordering doesn't matter anymore. We can now process this thing in parallel any further, and we enrich, not enriched. At this point, we parse the DNS packet, convert timestamps, and now we have a complete event. At this point, it's a complete event. It gets turned into protobuf and again shipped off the host. Now, in case you're wondering where the metadata for this process enrichment comes from, that too is captured with BPF. So we're tracking in memory, tracking process creation, exits, and forks. So that's how we maintain the representation of the process state in memory, allowing for fast enrichment. So I have to briefly talk about filtering. Since efficiency is one of our main goals, we have to keep the amount of noise in the system to a manageable level, really. Depending on workloads, and some services are quite heavy in that regard. So when you think about attaching a BPF probe into the kernel and that running constantly, it can create a lot of noise. So we want to filter. Where do we filter? Preferably, we want to filter as early as possible, and that means in the BPF probe. And we do this. Now, unfortunately, not everything can be filtered in BPF because BPF is very limiting in what you can do in it. So, evaluating a regex isn't an option. There's other things that don't quite work there, so it's very difficult to do. But things like muting a process, that could be done in BPF. It would prevent the event from even being emitted to user space, which is nice. There's no further processing. The kernel just carries on. Now, if we can't do this, then we can at least apply more complex rules, like as I said, regexes and so on, further in the pipeline during processing once the packet, in this case, is parsed. So we can drop it. And the last bit where we want to reduce noise is via dedupe. Imagine a DNS query being made multiple times per second. There's no real value in knowing that the same process made the same query hundreds of times. So we dedupe as well before shipping off the host into the agent, into the collector, the next stage. So there's 3 layers of filtering, and that's quite important to just keep things under control. Now, I mentioned BPF sort of in abstract terms so far. I want to show you an example. Cool. So this is an example of what a BPF probe in C code looks like. So you can see, well, it's standard function, looks like it. There's a few things I want to highlight here. At the top, you see the type of probe it is and where it is attached in the kernel. So this one is going to be called every time a process forks on the system. So once the probe runs, it will, in this case, read the PID from the current process, the child process and the parent process. Then it will build a structure and on the ring buffer and ship it into user space, and that's it. And then the probe returns, and the kernel just carries on as normal. And the user space then processes this data. So this is really a very minimal overhead onto the kernel. It only adds a few instructions to it. It's hardly noticeable, even with performance tooling. And we don't want to impact the host, of course, so we have to be fast. One thing to note here is that BPF is very modular, so it all looks like this. It's just a function, typically, without complex dependencies like you would normally see in standard C code, which helps with maintainability, of course. Now, to be complete, I want to show you the other second method I mentioned of getting data off the host is reading from the OS. We call them scheduled jobs. These are really just nothing special. They're just functions, Go functions that are called on an interval. So in this case, when it runs, basically it will collect whatever data it needs. So this one reads the proc modules, it then turns it in a protobuf, and again ships it off the host for aggregation. Dedupling happens here too, because when you run something on a schedule, like the packages installed on a host don't change very often. So if you run it like every hour, there's no need to send a record every hour if it hasn't changed. Now, we're moving off the host now, so the data acquisition is done. Now we come to the aggregation layer. We call this the collector. Basically, this is the middle part of the 3 layers, and let's zoom into this. Now, this is the thing that processes all the records shipped off the hosts by agents. It's sort of a central component. So fundamentally, its job is to receive a stream of records, events, or otherwise, from a large number of agents in the fleet. Then it demultiplexes them by record type, and then it stores them, of course. So if you can read this, yeah. So on the right, the table A and then table B, this just could be a DNS, all the DNS records, it could be all the process records or packages and so on. So I haven't talked about the mechanism yet that we use to ship records from an agent to the collector. It's quite important because it goes over the network. So we've chosen gRPC and protobuf here between agent and collector because gRPC uses HTTP2, so which only opens a single connection, which is nice. It's extremely well supported in Go, so we get authentication, retry, everything out of the box. And protobufs can be packed very efficiently. It's a binary format. Now, could we have done this with a standard JSON API over HTTP? Yes, absolutely. But it's a lot less efficient at that point because you're shipping JSON, which has a lot of overhead. And also you would have to maintain like connections, there's error handling and all of these things. We get this out of the box for free with gRPC. So no need to do this manually. Now, another thing I want to highlight here is that while the collector receives protobufs over the network from agents, it produces as output Parquet files. Why Parquet files? I will talk in the next slide a little bit. Now, the thing is with Parquet is that you need a schema to write it, this structured format. So you need a schema. Now, we have a protobuf, we have a Parquet schema, and do we want to maintain 2 schemas? Not really. So the best way to handle this situation is really to generate the Parquet schema on the fly. That's what we did. Whenever the collector receives a protobuf of any kind, it will just generate the Parquet schema that matches it on the fly and write the files that way. That keeps the maintenance overhead to a minimum because we don't have to maintain 2 schemas. We don't have to touch the collector at all if we add a new record or something like that. So just adding a new event to the agent would be trivial because you just add it as a protobuf send it to the collector, and the collector knows immediately what to do with it, even if it hasn't been changed. Now, one thing I'd like to highlight here is that the collector, the central component, is stateless. That is possible because all the records that are emitted by the agents are fully denormalized, so they're fully self-contained, and there's no need to correlate with other records or anything else, like add any further processing, no further enrichment. This data can just be stored as is, as it comes in from both above. Many other solutions perform processing at this stage. Now, what do we get for keeping it stateless? Simplicity, like most of all. That's one of the goals, after all. And it improves reliability, of course, as well. It's extremely fast, and we have some numbers for you later. And it allows us to scale to any size, really. We're just adding more hosts, and it just scales that way. What if it wasn't stateless, like if we did additional processing, things would get really complex at this stage, because you would have to like build a Hadoop cluster and run Kafka and Spark, perhaps, and things get out of hand really quickly. Much higher maintenance. So doing all the enrichment inside the agent really keeps the processing to a minimum, and it's really simple. Now, let's move on to the last of the 3 layers. That's the storage. So I mentioned Parquet. Why do we use Parquet? Well, it's column-oriented. It's very fast to use, very fast to access by different tools. It's very efficient and has a lot of compression and encoding schemes. So it reduces the volume quite a bit, which we need. And most importantly, though, it is well supported by all the big data tools out there. So pretty much anything can read Parquet files. So that was one of our requirements. We want to be able to use this data in many different ways, like real-time monitoring, retrospective, like we want to export it somewhere. So we want to have access to the data. So the data that comes in from the aggregator is really just a stream of Parquet files. It's grouped by, partitioned by type and day. I think there's an example prefix in this slide. Yep, if you can read it. Now, as I said before, this is also where we differ quite a bit from commercial solutions, where there's a dedicated UI, and the data is often hidden behind it. No, this doesn't even have a UI, so it's bring your own, basically. Just there's all the data. It's in a format that's very compatible, and you can analyze it with a number of different tools. Now, we talked about the agent, so the collection, the agent, collector, and storage. Now, I want to show you what an example record looks like, what an actual event collected from a host looks like. Now, I cut off a lot of information here to make it fit. So this is incomplete, but it should be enough. So there's really 3 main parts to it. This is just formatted as JSON, so I can read it more easily. So there's information about the asset at the top. So it would typically be a host name and some sort of asset identifier, wherever this came from, this event. The second is the enriched process list. This is basically saying that this is the parent process, and then there's the grandparent process, and then all the way to PID 1. This list is actually, if you walk the PIDs, it's truncated, so it won't fit. And the last bit at the bottom, this is where all the event-specific fields or the event-specific data lives. In this case, this is a process event, so a process was opened. So it would have things like the command line that was used, the environment variables, the user, and so on, and current working directory. And with this, I hand it back to Eknath to talk about metrics and benefits.
All right. So just as a reminder, our objective was to create an efficient, reliable, cheap to operate solution which covers a lot of customization, optimization that we really like to do. And this solution has been running for over a year at Stripe in production now. It covers over 100,000 nodes at any given time of the day. And the in terms of an achievement, I'd say it's pretty cool that a vast majority of the nodes consume less than 1% of the CPU. And the total number of records produced a second is around 180,000. Of course, there are spiky situations and whatnot. This is just the average I'm talking about. And thanks to the simplicity of the design of the collector, all of the collection only requires active 64 vCPUs. So in a typical AWS machine, that would be just 4 boxes, although we have provision for spikes and the likes of that. But this is what is actively being used. And cumulatively, again, even though the number of records is 180,000, and you saw that the enriched process metadata with the JSON blob is pretty large, we use Parquet, and that results in a pretty significant drop in the overall sizes. It results in around 8 terabytes a day. So these are just some numbers, but I'd like to highlight a very practical advantage of creating such a tool. People who have worked in enterprises and have worked on security migrations have this very real practical experience. Now, AWS very actively discourages usage of IMDS v1. But the question is, how do you go about finding who's using it and what you can do about it? One option is to grep your static code. The problem is you have third-party binaries, you have dependencies, you have dynamic path generation. There's no way to reliably find out who all is using grep. The other is to get real hard about it, deploy sysdig, and it will give you the right answer. But unfortunately, it's a local tool. You have to deploy it at scale, collect all this data at scale, analyze all this data at scale. Super painful. Third option is YOLO, test in production. Just disable IMDS v1, find out who breaks, and then watch who complains, and that. The other option is to use AWS metrics. Now, the problem with AWS metrics is while they are accurate, in at least our context, on a typical EC2 host, we have processes, binaries that are owned by different product teams, different service teams, which means AWS is only going to give you host level information. It's not going to give you which process is accessing IMDS v1, which means attribution becomes hard to which team do you have to go and say, all right, database team, you got to change it to IMDS v2 and stuff like that. So that is a problem as well. As you might have guessed, our solution, we just had to add a eBPF probe that monitors traffic on the local link address and convert it into a protobuf, just a bunch of strings, and ship it off to the collector. The volume was very low, as you can imagine, compared to something like a socket event or file event. And the best part, an additional advantage of doing something like this is that it very naturally integrated with our data tooling. So you could draw graphs, you could see that, over time, how the usage is reducing. It was just a real win-win sort of an outcome of this. Yeah, with that, I'd like to talk a little bit more about the investment, because earlier when we were talking about what it takes to build a custom solution, one of the things was to talk about the licensing cost, the expensive at scale. In our specific situation, getting to POC took about 3 months, one person, that was Frank. And in about 6 months, we got it deployed on production. And currently, I actively maintain it and make improvements. So that was sort of the investment. But I'd like to highlight another important thing here. It is this, that thanks to our operating system and infrastructure teams, at Stripe, we run only a handful of OS versions and a handful of kernel versions. Had it been a lot more, and had it been like wild, we'd have to do a lot more testing, a lot more reliability exercises, efficiency exercises to be sure that our thresholds are met and not breached, which makes a humongous difference in the development time, the quality of the solution. So, which is why I think which was an important contributor in this case. The other thing is that as you saw, almost all of the solution is built on extremely stable modern technology like eBPF, protobufs, gRPC, Parquet. I think really leveraging these very standard and stable solutions has helped out in our situation here. So the return on investment. This is all on the basis of running this in production for the past year. We had one minor incident in a very small set of hosts. There was a kernel bug, and it led to some crashes, but that's just been this one situation. Compared to the evaluations that we had done against standard tooling, all these OS query-based tools, it requires a lot less CPU, a lot less memory. Memory specifically because of the usage of the ring buffer, which bounds the number of elements that can be in memory, so nothing can overwhelm it, and a lot of such design optimizations. Currently, it drives a large part of the compliance requirements. Almost all of the vulnerability management relies on this being the source of truth for the entire org. And as you saw in terms of flexibility and customization about the IMDS one, you can add arbitrary events. You can answer operational shaped questions. Yeah, that has been a real win for us. And lastly, at Stripe, because we're a payment processing company, you can imagine we have cardholder data. We have all these very sensitive payment processing environments. And it's pretty awesome that we're able to 100% trust the code. I mean, really, trust me and him. But I think that is a real win here, too, that you don't have to trust third party. There are no risks of supply chain attacks, that sort of stuff. So in conclusion, I'd like to say that our experience has been that getting visibility, security visibility into your fleet is not that hard. We did, and I hope that so can you. Questions? Oh.
When you first developed this, was this kind of like your first project using eBPF, or had you had experience with that?
The question was this our first encounter with eBPF, besides some very basic Python testing? Absolutely. Yeah, this was the first. Yep.
So for your communication paths between your data from your collector to your storage, or even from your agent to your collector, did you ever think about using things like OpenTelemetry instead of just going with gRPC and protobufs? Because OpenTelemetry does support gRPC and protobufs, for example.
You want to answer that?
I haven't really considered it.
You said you have or you have not?
No, I have not. Okay. No. And to be honest, OpenTelemetry is a bit of a sore point in our monorepo. So I don't know if anyone has had some experience with that.
Why so?
No, the constantly breaking dependencies. So OpenTelemetry has a very bad rep in Stripe at the moment. As a repo, like the dependencies were not managed properly, and it constantly broke it.
Okay, thanks.
So, but yeah, we have not considered using that. So we wanted to be the most flexible, and that really means like protobufs for ourselves. Yeah, and we can adjust to what we need.
And I think another point here is also that OpenTelemetry would be one more layer on top of the native tooling, right? Like you have gRPC and all is natively supported. You have the OpenTelemetry would be another level of import. We didn't really see the need for that. Yep.
Yep. So you mentioned earlier in the presentation where you talk about applying filters to eBPF, like at the beginning. How do you, field that from, I guess, your monitoring teams and decide which filters go in, and then how do you apply them throughout your fleet?
I don't quite understand.
So you have like your eBPF filters in the beginning where you want to like exclude processes and things like that. What is your internal process for validating whether something should be excluded or not? And then how do you distribute those changes out to the fleet?
Right. So the first level of this would be to deploy it on a small set of hosts, collect data, and see what is noisy. Because our objective is not to actively discard data, it's to reduce noise. Right. So first step is to identify the noise. And once we have sufficient selection of that, we, as Frank mentioned, we had a deduplication layer as well to keep the unique data, but not discard everything. The last step would be to talk to those guys. That's the threat detection team. Can you wave? Yeah, so they are the subject matter experts on what can and cannot be discarded. That's essentially the loop. So the question was, how do other developers extend this Bigfoot? So at Stripe, we have a monorepo, so people can just open PRs. That's not a problem. But in terms of practice, we work very closely with the people who have. And in fact, the IMDS was created by someone outside of us. We are definitely the reviewers, though. Yes. So we basically keep a hash of the event, and we maintain a counter of how many times it has occurred, whatever is unique, because obviously adding timestamp would make it non-unique. So we keep the relevant bits in memory, and like depending on what sort of event it is, we allow 100 duplicate events an hour, because even the number of events is a relevant bit, right? Like a DDoS sort of a situation. So we certainly keep track of that. But depending on the event, it's a time-based and a counter-based limit. Yes.
To what extent can this tooling and infrastructure be used for like profiling and like performance measurement like use cases?
So I think eBPF is obviously very commonly used for profiling and performance, but that also goes into the depths of a lot. As you can see, like our probes are very specific to processes. We don't monitor what the process is doing in terms of memory allocations and CPU usage or performance counters or any such thing. So, and this is meant for scale, right? And typically these profiling tools are like very specific to a specific use case. So while the eBPF might be the commonality there, I don't think this is directly applicable in that. Nothing stopping you from, but I don't think it would work out very naturally in that. Because you want iterative development and all of that there, right? Like you find the first bottleneck, then you go into the next one. And yes? It's native EC2 hosts. In fact, it's physical boxes, it's micro VMs, and container-based environments as well. Yeah. Actually, exclusively Linux. Yes?
Do you use anything special to learn eBPF or just trial and error?
Just the resources that were listed in the thing, in the slides. Oh, sorry, yes. The question was, what resources did we use for learning eBPF? And that was primarily just the resources that were mentioned in the slides.
Lots of Googling.
Drinks. Okay, thank you.